For many years, scientists have used a method called neutron scattering to study what happens inside materials. They fire neutrons, tiny neutral particles, into a sample and observe how they bounce off. This helps reveal the positions and motions of atoms. But there's always been a strange interference effect that made some of the data confusing. Most researchers saw it as noise and tried to correct or eliminate it. That view has just changed, thanks to a research team at MIT in Cambridge, Massachusetts. In 2024, physicist Professor Ming-Da Li and his team, including postdoc Chuliang Fu and graduate students Phum Sirivibun and Artitaya Boonkurd, began looking at this interference in a new way. Instead of treating it as a flaw, they asked a bold question. What if this interference is actually carrying valuable information? The answer, as it turns out, is yes. And that insight may reshape how we study the quantum world hidden inside materials. The team developed a new method to interpret the interference seen in neutron scattering experiments. They discovered that the interference between two types of neutron signals, nuclear and magnetic, actually reveals how electrons interact with tiny atomic vibrations called phonons. These interactions, known as electron-phonon coupling, are crucial in many materials, especially those used in semiconductors, superconductors, and even quantum computers. Until now, scientists couldn't measure this interaction directly. They had to rely on indirect methods, full of assumptions. But the MIT group introduced a new technique called ANUBIS, short for Anomalous Neutron Nuclear Magnetic Interference Spectroscopy. ANUBIS uses the interference pattern itself as a kind of fingerprint to measure how strongly electrons and phonons interact. The idea was first published in a preprint in March 2024, and by June 2025, the research was accepted for publication in Materials Today Physics. MIT officially announced the breakthrough on July 24, 2025. To test their theory, the team ran a small experiment using an existing neutron source. The signal was weak, as expected, because current neutron beams aren't powerful enough to bring out the full potential of ANUBIS. Still, the results matched their predictions, confirming that the interference effect really does reveal electron-phonon interactions. In the future, this method could be used at next-generation neutron facilities, like the second target station planned at Oak Ridge National Laboratory. There, more powerful equipment could amplify the signal and allow scientists to study materials with much greater precision. So, why does this matter? With a better understanding of how electrons and vibrations interact, researchers can design new materials from the atomic level up. This could lead to more efficient electronics, better batteries, improved heat management in devices, and breakthroughs in quantum computing. But there's also a bigger idea here. This discovery shows how rethinking something that seemed like a problem can lead to progress. That interference effect, once ignored or dismissed, turned out to be the very thing scientists needed to see more deeply into the quantum behavior of matter. Thanks to the work of Ming-Da Li and his team at MIT, researchers now have a new way to explore the invisible forces that shape our materials and, potentially, our technological future.